Hey everyone. So we're here to talk about what are the last two special quadrilaterals in this chapter, and those are trapezoids and kites. So we're going to go through trapezoids first, kites second. So trapezoids themselves don't have a lot of super interesting things to them, so actually most of what we're going to talk about are going to be isosceles trapezoids. So in general, just starting off here, a trapezoid is a quadrilateral with exactly one pair of parallel sides. So it'll have one pair of parallel sides, one pair of non-parallel sides. The parallel sides are called the bases. So you'll have two different bases, and then the sides that are not parallel are called the legs. All right. So the thing that makes this a little complicated is that you have exactly one pair of parallel sides. So if you have a quadrilateral and you test one pair and you find that they are parallel, that does not make it a trapezoid because parallelograms also have a pair of parallel sides. So you actually have to look at the other pair as well, because if the other pair is also parallel, then this is a parallelogram. If the other pair is not parallel, then it is a trapezoid. Okay, so this is a shape that is not a subset of parallelograms, like rectangles and rhombuses, where we talked about last time. Okay, so again, the legs are the non-parallel sides. And a trapezoid has two pairs of base angles. So the base angle pairs are very similar to like the idea of triangles. Wherever you have the base, so here one pair of base angles are angle A and angle D. Another pair would be angle B and angle C. Okay? So just in a general trapezoid, these pairs don't really do anything useful. The pairs that are useful are actually the non-base pairs, so like A, B, and C and D are both consecutive interior angles. So these angles are supplementary. These angles are supplementary because A, B, C, D are transversals through these pair of parallel bases. Okay? So one thing that I could expect you to do is to actually show that something is a trapezoid. So trapezoids and parallelograms, all these things have to do with whether things are parallel or not. So this is a case where we're going to want to look at slope. So if you look at the measure of the slope of segment RS, slope, that's going to be 4 minus 3 over 2 minus 0. So this has a slope of 1/2. The slope of TO is 2 minus 0, 4 minus 0, which is 2/4, which is 1/2. Okay, so you see that we have a pair of opposite sides that are parallel. That's actually not enough, okay, because it could be a parallelogram. I mean, clearly looking at it, it's not, but, I mean, you know, bear with me here. The slope of RO is undefined, meaning is it a vertical line, and the slope of RT, just looking at it, I'm going to see that this has the slope of -1. Okay, so our answer is going to look something like this, actually. So ORST is a trapezoid because RS is parallel to TO, and RO is not parallel to ST. It should be ST. Okay? So the reason why this is a trapezoid is because we have one pair of opposite sides that are parallel and one pair of opposite sides that are not. Okay? So that's really it. That's the only thing we can really do with a normal trapezoid is just that definition. Now, isosceles trapezoids are trapezoids with congruent legs. Very similar to the idea of an isosceles triangle having congruent legs. And you'll see that the properties are also, this first property anyway, is similar to that of a isosceles triangle. Okay. So in an isosceles trapezoid, okay, the base angle pairs are congruent. Okay, so if you know that AB is congruent to CD, you can conclude that the base angle pairs B and C are congruent, the base angle pairs A and D are congruent. All right, this next one is just the converse of that. Okay, if the I want to say it's not plural. All you actually need is one. So if A base angle pair are congruent, then the trapezoid is isosceles. Okay, so you actually don't need to prove both pairs. All you need to do is prove one. The other pair are going to be congruent kind of automatically. By what? Does anybody remember? Old friend, the congruent supplements theorem. Okay. So these are going to be supplements. These are going to be supplements. Okay. This pair is congruent, so the supplements of the congruent angles are going to be congruent as well. Okay. The last thing here, now this is when things start to kind of bleed together and get a little difficult. The diagonals of an isosceles trapezoid are congruent. Okay, so this is actually a property that isosceles trapezoids share with rectangles. Okay, the difference being that in a rectangle is also a parallelogram. So the diagonals bisect each other. Here with the trapezoid, even though we have congruent diagonals, the diagonals do not bisect each other. So that's really the only, if you only knew that the diagonals were congruent, you can narrow it down to being either an isosceles trapezoid or a rectangle. You would have to look at something else about the diagonals as to whether they bisect each other or not. All right. So we have a stone and an archway up here. I believe if my high school, if my freshman year world history class taught me, I believe this is called a keystone. So we have a keystone and a stone archway here. It is an isosceles trapezoid. They tell us the measure of angle L is 85 degrees. So therefore, the measure of angle K is going to be the same thing as the measure of angle L. So that's going to be 85 degrees. Measure of angle M. Angle M and angle L are consecutive angles here. So they are going to be supplements. So there's going to be 180 minus 85. So measure of angle M is going to be 95 degrees. And again, because isosceles, J and M are base angle pairs. So angle J is going to be equal to the measure of angle M. And this one's also going to be 95 degrees. Okay. Mid-segments. Okay, you remember mid-segments of a triangle. A mid-segment of a triangle connected to midpoints on the sides of the triangle. Same idea here, but we don't really get a choice of the sides. The mid-segment is going to connect the midpoints of the legs. So if I try to draw a midpoint there, a midpoint here, and we connect them, okay, with a line that is definitely straight, that's going to be the mid-segment of the trapezoid. So the mid-segment of the trapezoid has a couple of properties that are reminiscent of that of the mid-segment of a triangle, okay? The first is that the midsegment is parallel to the bases. So the midsegment is parallel to the bases. Okay? In a triangle, remember, the midsegment is parallel to the third side. So similar idea here. And the other property of the triangle is the midsegment is half the length of the third side as well. Here's something similar. The midsegment is the average of the lengths of the bases. Okay. So now we can use that in a couple of different problems here. So if I have a midsegment, I know this is midsegment. I have M is the midpoint, N is the midpoint. This is a trapezoid. So the length of the midsegment, MN, is the average of the bases. So this is going to be PQ plus SR. So that's going to be half of 12 plus 28. These add up to 40. Half of that is 20. So MN is 20, and what units do we have here? Inches. Okay. All right. So the next couple questions here, I'd pause these, take a stab at them if you can, and then come back and play the video. So I think in an effort to try to make this video very short, I'm going to try to just explain these without writing all this down. If EG is equal to FH, is trapezoid EFG isosceles? The answer to that's going to be yes, because it has congruent diagonals. The real reason here is that we already know it's a trapezoid. It says, is trapezoid EFGH isosceles? And the answer would be yes. If the question had been, is quadrilateral EFGH isosceles, then you actually don't know if this is a rectangle or not. I know it clearly does not look like one, but we want to try to make decisions based on known information, not based on diagrams. So if we did not know that it was a trapezoid, we would be able to narrow it down to being a rectangle or an isosceles trapezoid. But since it is a trapezoid, we can definitely get away with calling that one a yes. Okay. Now here, if HEF, which is this angle up here, is 70 degrees, and this angle down here is 110 degrees, can we show that this is isosceles? And the answer again is yes. So you have to do one intermediate step, which is looking at these, again, these parallel lines cut by a transversal. These are consecutive interior angles. So they are supplementary. So if this is 70, this is 110. And now you have a pair of congruent base angles, okay, which leads this to being isosceles. All right. I think we have one final trapezoid question before we move on here. In trapezoid JKLM, J and M are right angles. JK is 9. All right. Find the length of the midsegment. So there's actually kind of two cases there. The reason why this is tricky is they actually don't tell you which ones are parallel. So JK LM. So if J and M are right angles, okay, we could have something like this, okay, and that would make these the parallel sides, all right? But it's possible to have JM and KL be the parallel sides. So if we did that, all right, so this is J, K, L, M. So if we had a trapezoid with parallel ones here, trapezoid parallel ones here, and J and K were right angles, okay, that would actually, if we were to continue this, also make these right angles, which actually makes this a rectangle, not a trapezoid. And also, if we tried to fill this stuff in, JK is 9, and if the mid-segment was 12, this segment can't be longer than this segment. They would have to be the same. So this whole construction is impossible. Okay, so it actually has to be oriented this way, even though the details were not given. So this would be 9. This would be the mid-segment, 12. Okay, and this length here is the unknown part, but we do know that 12 is the average of these, because that is a property of mid-segments. So 12 is the average of 9 and x. So if you multiply both sides by 2, we have 24 equals 9 plus x. And subtracting 9, we get the ML must be 15 centimeters. Okay. Now, on to our last shape, which is kite's my favorite shape. I feel like I say that a lot of things are my favorite, but this is definitely true. So a kite is a quadrilateral with 2 pairs of consecutive, means in a row, congruent sides. Okay, so rectangles also have 2 pairs of congruent sides, but they are opposite each other. It makes them a parallelogram. When they are consecutive to each other, it makes it a kite. Okay, and the book doesn't really assign words to these, but these opposite angle pairs are very important in different ways, and there's no good way to differentiate them. So if you think about them like an actual kind of like kite that you would fly, I call one of these where the congruent angles or the congruent sides meet the tip, and the other one the tail. Doesn't really matter which one you call which. But the idea is when you build in the diagonals, I'm going to refer to this one as the tip-tail diagonal. Okay, so the one that connects the kind of vertex formed by the 2 pairs of congruent sides. And then this is the kind of non-tip-tail diagonal. Okay, and each diagonal does something interesting. Okay. Now, the first thing that's interesting about kites, and you'll realize why this is my favorite quadrilateral, is that if a quadrilateral is a kite, the diagonals are perpendicular. Okay, so we have a quadrilateral similar to a rhombus. Remember, a rhombus also has perpendicular diagonals, and what makes rhombuses so interesting, or at least so difficult, is that they make 4 right angles, or 4 right triangles, and that's what we get here as well. So we get 4 right triangles, but unlike a rhombus, we actually have different right triangles. Okay, a rhombus gives you 4 congruent right triangles. Now, the other thing that happens is in a kite, okay, exactly 1 pair of opposite angles is congruent. Okay, and so this would be the non-tip-tail angles. Okay, so you have, again, where the congruent sides meet, call one the tip, one the tail. Okay, so the other pair of angles, the other pair of opposite angles, are congruent to each other. Now, the part that's not outlined in the book that's, I think, very useful as well, is that the tip-tail diagonal actually also is an angle bisector. Okay, and the reason for that is very easy to prove, because these triangles are congruent by side, 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 because you have side, side, and then the reflexive property of the side going through the middle. So by CPC/DC, these corresponding angles are congruent, these corresponding angles are congruent, and also these corresponding angles, right, if I do the big ones here, okay, are congruent. So those 3 pairs of angles are congruent by CPC/DC. So now what can we use down here? So let's find the perimeter of kite ABCD and the measure of angle CDA. All right. So what do we need in here? A couple of things. This is going to be a 90-degree angle in here, so we need to find that. All right, so the diagonals are perpendicular to each other. And then we can see here is that if this is 5, this is the altitude of an isosceles triangle, which bisects this side. All right. So not only are the diagonals perpendicular to each other, but one of the diagonals is bisected. Okay, so the tip-tail diagonal bisects the other diagonal. So if this is 5, okay, these are 45-degree angles up here. This actually is a 45, 45, 90 right triangle. So these sides up here are 5 root 2, 5 root 2. All right. And down here you would use the Pythagorean theorem to find the missing side, or you would recognize that this is a 5, 12, 13 right triangle. So my perimeter is 5 root 2 plus 5 root 2, which is 10 root 2. And then 13 plus 13, which is 26. So the perimeter is 10 root 2 plus 26. Okay? And now to find the measure of angle CDA, okay, I'm actually going to look at these as angles separately. So the measure of angle CDA is the measure of angle CDB plus the measure of angle BDA. And the reason why I want to look at them separately is that CDB is 45 degrees. All right, so that's just kind of given. And the measure of angle BDA, this angle in here, I don't really know what it is, but I could find it using inverse trig because I know the sides of this triangle here. So for instance, the sine of that angle is the opposite side over the hypotenuse, so it's 12 over 13. So the measure of that angle is going to be the inverse sine of 12 over 13. So you do want to make sure that your calculator is in degree mode, right? So the inverse sine of 12/13 is about 67.38 degrees. All right, and when we combine these together, we can find that the measure of this angle is approximately 112.38 degrees. All right. All right, last bit of practice questions here. So in a kite, the measurement of the angles are given, find x, and then which ones are congruent to each other. So this one is pretty straightforward. All you need is the property of a quadrilateral, which is that the sum of the 4 angles in a quadrilateral is 360 degrees. So you solve that, this gives you 75. So this is 25. So it's actually the 75 degree angles that are congruent to each other. All right, so that one's pretty easy. Now here, finding the measure of angle K, in a kite, these are my tip and tail, which means that the non-tip tails are the angles that are congruent. So the measure of angle K is the same thing as measure of angle 8. So that's going to be 88 degrees. No work necessary really there. Here, J and L are the tip and the tail. So M and K are the ones that are congruent to each other. So I have to kind of use, again, the fact that the quadrilateral adds up to 360 degrees to solve this for x. And this gives me that x is 125. So the measure of angle K is 125 degrees. Number 8, the exact perimeter in simplest radical form. All right. Let's see. These are perpendicular, so these are all right angles. So VS is the square root of 9 squared plus 8 squared. So that's the square root of 81 plus 64. And that is the square root of 145. And that actually cannot be simplified. So 145 is 29 times 5, so there's no perfect squares in there. VU is the square root of 9 squared plus 7 squared. So that is 81 plus 49. 81 plus 49 is 130. 130 is 2 times 5 times 13. So none of those are perfect squares either. So actually neither of these radicals can be simplified. And you can only add them if they're the same, so they actually can't be added together as well. So the perimeter here exactly is just 2 of these root 145s plus 2 of these root 130s. That's it. That's as simplified as it gets, believe it or not. Last 2 questions here are mid-segment questions. Okay, so again, the mid-segment of the trapezoids is the average of the bases. So 2x plus 8x plus 3.2 divided by 2. These are actually all kind of even, so I can divide these in half. So this is 10x, half of that is 5x. 3.2, half of that is 1.6. We can subtract the 1.6. We have 5x equals 15.5. Dividing by 5x is 3.1. And here our bases are running vertically. So 43 plus 4x, average of that should give me this 32. Don't really want to cut this in half, so instead I'm going to multiply everything by 2. So 43 plus 4x equals 64. If we subtract 43 from both sides, that's going to give us 21. And dividing those by 4, we get x is 5 1/4. Okay. Hope everyone's doing well. Good luck, and email if you have questions. Take care.